All right. I guess it's fair enough to start. We've got some people who have joined us already. So it is my great pleasure to have you all at this AILS Artificial Intelligence for Life Sciences seminar. And our today's guest is Lucas von Chamier. And Lucas did his undergrads at University College London in natural sciences and specifically molecular biology. And during his PhD, which is currently ongoing, Lucas, an amazing sort of twist of his abilities, switched to artificial intelligence and decided to apply this to microscopy. And this is exactly the kind of work that we're looking to kind of foster and to promote with artificial intelligence for life sciences. Artificial intelligence for life sciences has a forum where we exchange some opinions and chat essentially about how to apply novel AI techniques to life sciences and so on. So today we're hoping to get some cues of how this transition is happening and how smooth it can be for a life scientist to become an AI expert. And hence, without the further ado, Lucas, the floor is yours.
Thanks. Okay, I'll share my screen. Okay. Cool. I hope you can all see this. Arthur, can you see this? Can you confirm?
Yeah, it looks good.
Awesome. Well, thank you very much for inviting me to this, and Arthur, and thanks for everybody who came here kind of late in the day. I'm really excited to present this project, zero-cost deep learning for microscopy, which I've been working on kind of for the last year and even a little bit before, which is basically sort of now the main thing that I've been working on towards the end of my PhD. As Arthur has said, I'm actually a biologist. I have a little bit of a physics background from natural sciences, but by training, I'm really a biologist. And the motivation kind of behind this project and the idea behind this project is that this is the kind of tool for microscopy that I would have wanted to exist when I started in deep learning, and especially in deep learning for microscopic image analysis. So what this tool is, and that what I want to present to you today is kind of how to make it easier to use artificial intelligence in microscopy, and to allow more people to kind of harness the power of AI for deep learning, for microscopy. So let me get started. So why are we interested in deep learning at all? So as you know, in the last couple of years, there have been huge advances in deep learning, and basically it's a set of algorithms, or like it's a whole field that has sprung up over the last few years, maybe just the last decade, that has really made techniques available and possible even that weren't possible, a decade ago. And an example for this, what is very exciting, is self-driving cars, which basically use deep learning to recognize thousands of objects in real time and with almost human accuracy. And obviously, this is also interesting for other fields that have a high load of image data, which is coincidentally biology, which has become increasingly a data-heavy discipline. And that is why in the last couple of years, dozens of papers have come out that are using deep learning. And if I say dozens, I probably should say hundreds. Dozens have probably come out in the last month only. And so there's a huge interest in using deep learning techniques for image analysis. And loads of people are excited to use these techniques because they kind of allow avenues to analyze data that just weren't available a few years even ago. So I don't know what your background is in artificial intelligence or in deep learning, but I'll just give you sort of a quick background what I'm going to be talking about and what I mean by deep learning in this sort of in the context of my work. So if we look at how a classic algorithm, for example, would perform a task like denoising, what you would do is you would have a noisy image, you write your algorithm or you write a program that does some kind of denoising, that performs a denoising function on the pixels of that image, which could be a Gaussian filter, a convolution, or just brute force thresholding, and you will get a denoised image out of it. In deep learning, as you may know, you often use something called neural networks. That is the most commonly used form of deep learning, at least in microscopy, and generally is now the most powerful kind of paradigm for deep learning. And what you use is a training data set to kind of prime this neural network to perform your denoising task. Denoising is just an example that I use here for visualization. It can actually do loads of other things, which I will show later as well. But basically, you have a training data set that consists of training inputs that would be noisy and training targets, in this case, that would be denoised. And you usually need a big data set to train your neural network to kind of achieve a denoising operation as your normal algorithm would. How this works in practice is that your neural network will have layers that perform convolutions on your input images that basically work as feature extractors. So as your image kind of goes into the neural network, the network first extracts features in convolution layers, and then these convolutions are basically, as you get further into the network, more convolutions get performed, and you also get something called pooling, which usually just reduces the dimensionality of the data and kind of simplifies the data. So it basically becomes like a barcode. And that is something that your algorithm, that the deep neural network can read and then basically map onto your training target. That is just a very simplified kind of version of what is happening, but I just wanted to give like a quick overview and visualization. As you kind of have more layers and your network gets deeper, the more complex these operations in the network get, and that's when you kind of get deep learning. That's where the deep comes from the amount of layers that you can have in your neural network. So as you train the network, you kind of feed your training data set multiple times through your network, and your network will start getting better at predicting the kind of data that you want to get out of your network. So after maybe 10 rounds of going through the data set, your predictions might look a little bit crap, like this. And as you kind of add, or like as you kind of continue training the network, it will start getting better and better and reduce the error between its predictions and its targets. And at some point we'll reach a level where it can predict something that looks extremely similar to the target, and then is basically primed for the task that you will want to use it for. The problem with this is, one of the problems with this is that this is computationally extremely expensive. So it is not sort of a trivial task to perform these convolutions on large data sets, which is why you need, usually you need GPUs or graphical processing units to perform these operations. And without GPUs, this is basically, deep learning is basically not really feasible at the minute. And most algorithms will train days or even weeks, even with GPUs. Without GPUs, I mean, it would take months or years. It's a huge increase in computation power that has made deep learning possible in the last decade, really. The other problem is that as a biologist, if you want to use some of these really exciting techniques, usually you have to visit a GitHub page, which is awesome because you can learn a lot about how deep learning is implemented in practice and code. However, you will have to read tons of code to then apply a deep learning technique to your own data. This is quite scary for people that might be new to coding, that might not be computer scientists, that just want to use a deep learning technique on their data because they want to analyze a large amount of data using AI. So this is a little bit scary and is a bit of an obstacle for bioimaging to use deep learning. There have been some efforts in the community to kind of make it easier for users to get started with deep learning. And there are some amazing projects like CSB Deep, kind of based in Dresden, and Deep ImageJ and Elastic teams that sort of created interfaces that make it a little bit more user-friendly to get started with deep learning. The problem is that still to use this, you kind of need the power of GPU to train on your own data. So there are like a couple of obstacles in practice to get started with deep learning. It's usually not easy to train on your own data if you're not familiar kind of with the coding environment of deep learning. There's often no clear workflow, so how you get started assembling your data set and then kind of starting to train and then testing your algorithm once you're finished. Then there's often no proper protocol for testing if your algorithm is actually working as it should. And this has caused a lot of skepticism. So in the bioimaging community, especially when it comes to stuff like resolution. And an example is, for example, that you might have like sort of a low resolution input and an algorithm that can produce an amazing output that looks kind of like a realistic prediction. But if you compare it to the ground truth data, it might actually be completely wrong without you noticing. So really the community needs strong tools to kind of test whether their algorithms are working. And without them, there will be no trust in these new techniques. And this is already something that we're seeing in the community, that people aren't really convinced by deep learning. So in order to get it into the community, we need to have quality control. And the other problem is money, as I have already said about GPUs and GPU time. So this is kind of where we came in with our idea for zero-cost deep learning for microscopy. We wanted to create something that can reduce the cost of getting started with deep learning, make it more user-friendly, and make the results somewhat trustworthy, and kind of create a community that wants to know more about deep learning rather than dismissing it as something they can't trust. So the first step for this was that we wanted to use Google Colab, which is a cloud computing platform that gives free GPU time to users up to a certain limit. But this is perfect to get started with deep learning because you don't have to buy a GPU and you can basically spend as much time as you like playing around with it. So then we decided we wanted to adapt some cool networks that we were interested in for microscopy to implement it in Google Colab and make it into a user-friendly kind of platform. And so the applications that we were most interested in were segmentation and detection. And we've kind of applied or adapted several existing algorithms for this, including UNIT, which is sort of doing classic semantic segmentation. Stardust, which is a nuclear segmentation algorithm, and YOLO, which can classify objects in images. Then we do image restoration. This is basically what I've shown in the beginning as an example, which you can do denoising operations. We have noise to void and care, which are kind of the most famous ones right now, but there are many others, and some of which we are working on. Super resolution. So we have an algorithm called DeepStorm, which can basically convert SMLM or single molecule localization data into super resolution images. And finally, we have some algorithms that just basically perform complete deep learning magic that weren't really possible before deep learning happened, which is something like FNet, which can predict fluorescent labels from bright field images, which is obviously a really cool thing because you kind of reduce the amount of phototoxicity you produce when you image fluorescent labels. We've also implemented some generative networks that are kind of known for like deep fake stuff you might have heard of, which can basically predict anything from an input image. And we've sort of decided we wanted to play around, and the examples that we have are predicting nuclei from cell membranes or predicting super resolution images from diffraction limited data. But in theory, you could do anything with those. So really cool stuff. So now this is sort of the most important bit of this presentation. So if you are still paying attention, you can sort of, now is the time to really look. This is kind of where we, how we are implementing these networks. So if you go to our GitHub page, you will basically see the implemented networks. You can open them in Colab. And then what you will see is something like this that looks like a Jupyter notebook. This is basically how the platform works. What you then do is you create your own copy of the notebook that we have created and download the training data that we provide, or upload your own training data. We have created sort of example data sets for everything, for all the implemented networks. So you can test all our notebooks with the data that we provide. This is all kind of to be found on our GitHub page. And for example, for Stardust, you can then upload this data to your Google Drive. So what you need is a Google Drive where you can upload your training data sets. We give like really clear instructions how you can assemble your training data sets. This is usually something that can take a little bit of time, not just the upload, but also the assembling of the data set. And then once you have your data in your Google Drive, you will be able to basically get started immediately with deep learning. You don't really have to do anything else. You can, for example, check that you have GPU access. That's sort of the first step in each of the notebooks. Then you connect the notebook to your Google Drive, which is basically just basically following a few instructions on Google. And once you have kind of done these very simple steps, you are ready to go. The Google notebook layout is sort of basically gives you this folder structure where you can see everything that's in your drive. And as you can see here, for this notebook, for Stardust, we have our data set ready here on the side. You can install everything that you need, which is also useful because if something goes wrong, you can just start again. You don't have to download anything to your own machine, which is also sometimes quite useful because there will, if you have version conflicts or something like that, you sometimes can run into trouble, especially if you're using different kind of neural networks or something like that. You don't have that trouble if you have like a dedicated notebook environment for each neural network that you're using. So that what you just saw is basically putting in the parameters that you want to use for training. Then you create your training objects. You can have a look what your training data set looks like. In this case, this is a segmentation map, and then you can just start your training. This is all speeded up here. This can take a few minutes or even a few hours. And then an important step in our notebooks is to perform quality control. This is kind of, I'll go through this in more detail in a sec. And basically, as you put in your test data sets, you can then test how well your trained model performs on the data, on new data that you haven't trained it on, which is kind of an important step here. You can test for the overlap in this segmentation algorithm. And finally, you can also use the notebook for batch processing. So once you have your trained model, you can just inside the Google notebook, you can analyze hundreds of thousands of images on the algorithm that you have trained. And all you need to do is basically type in the paths of the data and the path of your model, and then tell the notebook where you want to save the data. And that is all you really need to do to get started with these notebooks. The notebook that I've shown here is for the Stardust in 2D, which is just for nuclei. This is what the output then looks like. And all the notebooks have the same layout. So whether you're using this notebook or any other notebook, it will always kind of follow the same workflow. So to summarize, what you need to do to use the notebooks is prepare a data set for which we give instructions, prepare the network for training, which means putting in the parameters that you want to use for training, then click play. Then you can evaluate your training, your trained model on your test data set, and then do inference on new data or like the data that you're interested in processing. What I think is really cool about these notebooks is that because it's cheap and free, you can basically do this process over and over again. Here's a little bit more about the quality control for image to image kind of algorithms like denoising. This is the kind of data that you would have. And now you can compare, for example, your target to your prediction. This is just a different type of quality control compared to the one that I've just shown. We have different parameters that you can test, for example, the mean squared error or the structural similarity. And we have a couple of different metrics as well that you can test. So really what we want to try to do is allow people to test how well their algorithm performs compared to, for example, the target data or the ground truth data. And this can all be done within the notebooks. And then basically you can play around. And I think this is like one of the great things about these notebooks, which is that you can do this as many times as you like, and you don't have to pay for it before you do your actual processing. So what we've done is, to summarize, we've reduced the cost of like getting started with deep learning. We've tried to create like a user interface that is makes it easier to get started using deep learning, and created quality control steps that make it easier to trust deep learning methods. So here's a small summary of the networks that are already implemented, fully supported on our GitHub. We're also working on implementing more methods, for example, instance segmentation, which is sort of the next, is a combination of classification and segmentation, where basically you're creating masks of the objects that you're detecting. And we're also working on stuff, on even more stuff that's coming up with cooler algorithms that we're interested in to kind of boost what we can do. And we also have some collaborators that are already using some of these algorithms. This is an example of a data set that Christoph Spahn analyzed. He's a bacteriologist. And this is an example where he's basically just been studying how many cells are dividing in his sample. And this is by hand really difficult to do. But if you have an algorithm that can kind of start analyzing this data, then you can kind of automate this pretty quickly if you have a good data set to train with. And this is kind of going full circle to what I showed you at the beginning, right? We've also seen that the community has kind of started to take up some of these notebooks, and they've tweeted about it. And I would just encourage you, if you're interested in this, to go to our GitHub and try it yourself. You can either use your own data or play around with the data that we provide. And that's it. So I would like to just give acknowledgements to some of the people that have been working on this project with me, especially the people from my lab, Ricardo and Roman, who've been, Roman especially has been really essential for this project. And the other one being Guillaume from the University of Turku in Finland. So Roman, Guillaume, and I are the people that have been developing this project. And we've had loads of other great collaborators that have helped us implement some of these methods into our notebooks. And I'd also like to thank the MRC, because they've been funding me throughout this project, and my institute, the LMCB, of course. And that's it. So thank you, the people that came to listen to this, and I hope like you could take away a little bit out of this. And I'll be happy to answer a few questions if you have any.
Wow, this is amazing. Thanks a lot, Lucas. Super cool stuff. Definitely advisable to check out all those links. I guess you can maybe provide them later on for me. Then once this recording is going to be available, I'll make sure that they are accompanying the talk. So I would like to maybe ask if anyone has a question. And I'm going to allow you to unmute yourselves. So please feel free to just maybe go ahead, unmute.
Yeah, can you hear me? Actually?
Yes.
Hi, Lucas. Thanks for the talk.
Hi.
Yeah, so I was just wondering. So, how do you deal with like different inputs essentially from like different microscopes? Do you somehow standardize, or do you provide tutorials on how to do that? Like, I don't know, like 16-bit images converted to some sort of floats or stuff like that.
That's a good question. So actually, there is different neural networks will be adapted to different kinds of data, and some of the algorithms that I've shown will actually only work at the moment, for example, with PNG images, and others will only work with TIFFs. There is at the moment, we're working on a Fiji plugin that is sort of like an it's like supplementary kind of software to our project, which we hope we can sort of help people assembling the data sets with, because really, like, once you kind of get started with this deep learning, like once you understand it, the most difficult aspect of this whole thing is like creating a data set, right?
Exactly.
That takes hours and hours and hours. And yeah, to get the right kind of data set is really important. And at the moment, we don't really have specific software or tools that will help users to make their data, but each notebook, so if you go into the notebook, there will be instructions on the data, the type of data the notebook will definitely work with. So it will say what file format you need, if it's 8-bit, 16-bit, or something else. But usually it should work with raw images, so you don't need to convert anything into arrays or anything. So I hope this answers your question.
Yeah, thanks a lot. I'll give it a try for sure. Yep.
I was also wondering if, since you're running it on GitHub, if you're, let's say, welcome merge requests from other people, from other collaborators across the academia altogether to, build it into a bigger sort of repository, if you will, where you can not just have the code sitting, but also have the code runnable. I wonder if you look into build something like that.
Yeah, I mean, obviously, like there are, like, what I haven't really covered are some of the limitations of Google of using Google Colab. There are, like, obviously some limitations of using a free service, but yes, the code is basically completely open and anybody is welcome to use it. And there have already been a couple of people that have basically made their own zero-cost type applications. And we welcome anybody who wants to collaborate with us and to merge or pull anything that we have on GitHub, just to get in touch with us. There's also another project that we're working with that is kind of trying to build a much bigger kind of database of deep learning models in AI, which is called BioImage.io, which is driven by Wei Yang, who I think he works in Stockholm. And he's basically building this big repository where everybody who has ever trained a deep learning model for microscopy can put up their trained models and data sets or notebooks. And we are also, thanks, Martin. There's basicically whatever you have trained or data sets you have assembled, you can upload there and can have other people use it. And we've been working together with Wei to kind of make our notebooks available there too.
And that's super cool.
Yeah.
I think Martin had a question as well. I'm not sure if he wants to ask it himself, or I can read it out as well.
Sure.
Yeah, I can ask you. Thanks, Lucas. Great talk. So yeah, my question was, I suppose, following on from, Colab has some limitations, and often we're dealing with large amounts of data, and there's, the limiting factor becomes piping the data up and down. So I guess the nature of the notebooks and so on, it looks like it should be something that we could run locally on our HPC, or are there any gotchas that we would need to sort of consider that might make that harder than we think?
Yes, so great question. Yes, there are definitely data limitations that also apply to Colab, but the notebooks can be run there are instructions on Colab on how to do this. There are like a couple of extra steps of difficulty involved in running them locally, but we have done it, and it's definitely very feasible. The other thing that you can do is like you can just use the code or the notebooks and use them in like more high power cloud computing platforms. So they run relatively smoothly in other environments, not just in Google Colab. So if you want to kind of overcome some of the GPU limitations or the RAM in the Colab notebooks, you can port the code and use it relatively easily. Yeah.
I could imagine something like that would be possible through just connecting to a local environment, right? Sorry, Martin.
Yes. Sorry. Yeah. I mean, you can do that. I mean, I suppose the only disadvantage is that obviously the notebooks are adapted to the Colab environment, and the nice interface that you only get it in Colab. So that you kind of see only the cells without the code, for example. Obviously the code is right behind the cells. So if you want to see the code, you just double click on them. It's right there. And if you port it to something local or a different platform, the interface kind of is gone, but you can still run all the code pretty effortlessly. Yeah.
Fair enough. Martin, sorry, I spoke over you. Did you have anything to add?
No, I was just saying thanks for answering. That was very useful. I think it's something that we've, it's definitely something that we're looking to try on our local at the Crick. We've got a really nice big HPC and lots and lots of data that we need to analyze. So.
That's awesome. I mean, if you have any trouble doing it, or if you're really successful doing it, we definitely like to hear about it.
Yeah. Sure.
Because it's really useful. Like we'd really like to know if this works, if we can make this work locally well as well.
Yeah, we'll keep you posted.
Yeah, great. Thanks.
Awesome. Are there any more questions? I think, yeah, Evgeny has a hand.
Yeah, thank you very much for your talk and very useful tool. I have just a technical question. I know that Colab will have limitations on running time. How have you managed to overcome this? Just one.
Yeah, good question. So, I mean, there are definitely limitations when it comes to runtime. I mean, I guess the amount of data that you can use on Colab is limited, but like is usually large enough to get the networks trained pretty well on your data set. So you can, I don't know, if you have like a 20 gigabyte data set or something like that, the Google Colab notebooks actually work pretty fine. But obviously in biology, like 20 GB is nothing. For those small data sets, it works quite well. If you have bigger data sets, I guess you need to run locally, but if you need longer run times, one thing that we have that I didn't show is you can also use pre-trained models in the notebooks and retrain them on new data. So if you run into the runtime limitation of 12 hours, which that's usually the runtime limit for Colab notebooks, but if you have the checkpoint of the 12-hour time point, you can upload that into the notebook. So we've implemented something that can do that, and then you can train from that point again for 12 hours. It is a little bit annoying for people that are used to training, deep learning algorithms for weeks. That's not something that this project is for. But if you have like something that you need to train for a few days and you don't mind, coming back and uploading the weights again and retraining, then you can do that. From like I think for all of the notebooks except one, I think like all of them have it that you can continue training. Yeah.
Awesome. Thanks a lot. And we actually are almost out of time here. So I would like to take this second to say thanks to Lucas again for coming over today. And please follow him on Twitter. And, he is a really nice and friendly guy. He is always going to help you out with getting stuff off the ground. So again, thanks a lot. Thanks everyone for joining today. Have a great evening, and looking forward to see you at the next AILS Talk.
Thank you for inviting me. Thanks everybody for coming. See you soon.